Okay, hello. This is totally optional footage in which I will go over all the unsolved problems of the practice midterm for this summer, Physics 204. So I'm talking about this document here, right? So we need that. We're going to try to solve it. You already have solutions that I have not corrected or updated or looked at really, but there's already some kind of raw solutions to the first two problems, so I'm not even going to address those. I will look at those to see if there's errors or corrections necessary later. I'm going to start with problem 3. There's a lot of reading. It's overly long. The real problem on the real exam, if it resembles this directly, if it's recognizable, it'll be much shorter and easier to read and stuff. But the first thing you're asked to do is here on page 12 of 20. So that's where we're going to start, on page 12 of 20. Right, okay, so we're going to start on page 12 of 20 going over. So what's happening in this problem is you've already been told that you took a bunch of data over a bunch of time, and the data that you took is sunrise and sunset times per day. You're taking this data every couple of days, and then from the time that the sun rose and the time that it set on any given day, you then sort of did a calculation, subtracted, and figured out the total amount of minutes per day that the sun was out, and you're graphing as a function. And then you made a graph of, in effect, after you sort of normalized this data, you made a graph of the percentage of any given, what you graphed was on the x-axis time, like literally throughout the year. The units of measurement originally are days. On the y-axis, you're graphing, you're charting, plotting for each given day, as noted by the x-axis, you're charting the percentage of that day during which the sun was actually out in the sky above the horizon, right? This percentage fluctuates throughout the year around 50%. It never gets up to 100%, never gets down to 0% here in New York. But anyway, you're charting it. And, you know, I think you roughly understand this concept already before doing this. That is to say, summer days, far more significant percentage of the day, far more significant than 50% is spent with the sun out. Winter days, less than 50% of each day is spent with the sun out. That's what we mean when we say the days are longer or shorter. So, all right, so you make a graph of that, and then you look at the graph, you look at the data on the axes once you scaled them and everything. And the first thing is that you look at a small chunk of this data, the data that you actually did take, and you're looking at a small enough chunk that you see that the data is not a straight line, it's curved and it's curving up. So it's like actually reasonable, very reasonable for someone to look at this data as you did in lab 1 with other data and say, oh, okay, that's not a linear relationship, but I'm always looking for the simplest possible relationship that I could hope and imagine it to be and test out. So I can't test out linear, but maybe it's quadratic. Someone thinks like maybe it's a little chunk of a parabola. Totally reasonable on every level to think that, and reasonable to want something to be a parabola because it's easier to deal with than many things. Okay, but if it is a parabola, then the motion being described by that parabola is not simple harmonic, does not satisfy the differential equation for simple harmonic. And that's what, in your first little mission here of the problem, that's what you're being asked to do, to show that since this full graph, when you zoom all the way out, clearly seems to be oscillatory, seems to be periodic, cyclical, you want to show that the function that describes it must satisfy that nature, that oscillatory nature and that harmonic nature, and a quadratic doesn't do that. So your first job is a theoretical one. And again, I apologize how much the backstory is so sort of big. You don't need all this backstory to understand that in this first part of the problem, subsection 1 and 2, you're just doing an isolated theoretical exercise to show, we're here to show, independent of any particular graph, to show that P of T, that this while it might very accurately describe the chunk of data that someone initially looked at in this story that you're told, you're here to show that it does not satisfy the differential equation for simple harmonic oscillation. And I'm going to do that right now. One last note. You might say, all right, if it's that straightforward a problem, why all this complexity? Like, why did you have to make the function look so wacky? Yeah, Verbaum, if it's just an exercise to show that quadratic doesn't satisfy harmonic, why the crazy exponent? Why the scientific notation? Because if a quadratic were to describe the data thus depicted, if a quadratic did accurately describe the data that we have before us, then this would be the numbers that give it the best shot of doing so. In other words, this is the most accurate way that you could guess a quadratic for the chunk of data that we have. Like, we're actually trying to build up equations here scientifically from data. That's what we do as physicists, as opposed to just like thinking that equations come from Moses and then just using them blindly. All right, so it looks complicated because it's like real in a sense, but whatever it is, I want to show that it does not. I want to show that this does not satisfy the conditions that it would need to in order for this to be a harmonic oscillator. In other words, I want to show that this does not satisfy d2p dt2 equals some constant, right? Like that. If that equation that I just wrote is an equation that must be true if the variable p is something that is oscillating harmonically. And I want to show that this equation does not satisfy this equation. Okay, so that's what I'm going to do right now. What does it mean to do that? How do you check? It means to take two derivatives of p with respect to time and see what happens. All right, so dp dt, the first derivative of this quadratic is power rule, right? Is 2 times that crazy thing in parentheses, that coefficient, and then bring down the power of t by 1. So it's 2 times the coefficient times t minus the derivative of the next term. The next term is a constant, doesn't have any t's in it, so the derivative is 0. So this right here is the first derivative. In other words, I should say this is all approximate, honestly. I mean, and approximate doesn't mean less real. It actually means more real if you think about it. We're admitting that this is like data oriented. Okay, so 2 times 1.5 is 3.06 times 10 to the third, whatever units. That's supposed to be a 0. Okay, 3.06 times 10 to the third t. That's what the first derivative of p is. Okay, but I don't care as such. What I care about, I needed that in order to get the second derivative of p. I care about that because the simple harmonic oscillation differential equation is a second order differential equation. It necessarily always makes reference to a second derivative. So I take derivative again. Well, what is it? This time it's just literally the number 3.06 times 10 to the negative third. That is the derivative, the second derivative of this original function. Now that's a very clean, nice, manageable derivative. Like, I'd love it if I was dealing with some function in the lab who looked like that, which looked like that. It's a constant function on some graph. It would be a horizontal line if I graph p that as a function of t. However, as nice as it is, it's totally not nice in the sense that we are looking for. Like, what was supposed to happen if this is an oscillator, if this were an oscillator, upon taking two derivatives, we're supposed to get back some expression of p, the original variable, right? That's the whole point. In this case, p was equal to some t squared thing. We should have gotten back a t squared if this thing were a solution. The fact that we got back something, excuse me, the fact that we got back something with no t's in it at all, well, that's a bad color, is nice for other contexts, but not nice for this. I'm saying then, in other words, I'm saying dp2, I'm saying dp2 does not equal some constant function of p, if p equals that quadratic thing. Okay, so we've proven it. We've answered question 1 of 3. We've shown that p does not satisfy the differential equation for harmonic oscillation. Therefore, the quadratic guess is a wrong guess if we believe the system to be an oscillator. So now we're saying, all right, let's assume that this new function, and let's assume, in other words, that, you know, if you step back from all the physics and just think, we're basically just discussing the normal natural context of daylight hours fluctuating somewhat rhythmically throughout the year. Like days are longer in summer, they're shortest in winter, right? They're on the rise, they're getting shorter and shorter in fall until they're really reaching a low point in the winter, and then they start getting bigger and bigger through spring and through summer. What do I mean by bigger? I mean the percentage of a given day during which the sun is visible, right? So if you think about the rhythm of the 4 seasons, like I hope it doesn't shock you to think it could be graphed like some kind of cosine, which the statists say that it is. So if we're now going to go with the assumption that, well, that certainly looks like this variable is oscillating in a nice way, like it's not just going back and forth, but it seems to be going back and forth at some constant rate, some rate that doesn't seem to be affected by how high or low the graph is. I don't know if we could say that. So if we assume that now, let's assume now that p looks more like this kind of function. Now it says, assume that, show if that's the case, it will satisfy the differential equation. Okay, this is total practice. Like this will be on your exam, but this is a review of something we've now done a million times in class. I'm not saying that to say it's easy or that you should have no issues with. I'm just saying it's not a trick. We're just asking you here to kind of regurgitate, if you like, or recite the little mini check that we've done a million times to, I shouldn't say that we've done numerous times to show that this does solve this. Okay, so we're not asking for some tricky new version of that. We're just saying, do the legwork. We've now shown that we've now shown how our checking system works, that we've rejected one function. Now let's allow through a different function. Let's take the first derivative. It's just showing you that this test is fair and consistent. It's a filter. It lets some things through and some things it doesn't. If we take, we're assuming that P of t now, we're assuming is our good old, you know, it's what we've been studying in class. It's just using P instead of X or something. And we want to be very flexible about that kind of thing. So if we take the first derivative, and we get negative P naught omega sine omega t plus phi. In other words, again, this is just a trigonometric derivative with chain rule, right? So the omega comes out and the negative sign comes because the derivative of cosine is negative sign. So now we've taken another derivative because it's all about checking the second derivative. All of physics is about second order differential equations, F equals ma, for example. So we do this again. So the omega comes out again from chain rule. The negative sign doesn't flop because the derivative of sine is straight up cosine. So we get negative P naught omega squared cosine omega t. This is the standard check that led us to believe in cosines in the first place in class. We're saying, oh, okay, if we take two derivatives now, the cosine, oh, came up again. That's nice. That's a nice feature of cosine that when you differentiate cosine once, you don't see cosine anymore. But when you differentiate it twice, it comes back at the expense only of some constant term, right? And a negative sign. Well, heck, that's exactly what we want. If we can recognize that multiplication is commutative. So this above expression here, I could have written this way. This color changes a little bit unmotivated. And so I'm saying, look at what we have here, folks. That's P. So apparently, d2p dt2 does in fact equal negative times some constant times the original P itself. Yay, it checks. Okay, we're just checking again something that we've in principle now known for a few days. That checks. Again, every time I write omega squared on the paper, I'm saying in English some constant. That's totally how I want you to think of it. Omega squared is just some constant. Don't be thrown by the squared. It doesn't make this some fancier function. Like every time I say omega squared, I could just be saying omega squared, like just a new letter that we made up in the alphabet called omega squared. I could even just be saying omega. The reason we square it is because of this thing that we find out, where later on the square root of whatever that constant is the angular frequency of the oscillator, right? It's like, it is hindsight that we call it omega squared. It makes more sense once everything else makes sense to you. But until it makes sense, just think of omega squared as its own little constant called omega squared. Okay, but anyway, so this checked. So this is good. This is a good indication that cosine is nice. So that means we've done question 1 and 2. So now go to the next question. The next question now, look at the graph and the data. All right, now it wants us to compute, now it wants us to start taking this data seriously. If we're now saying, oh, we've just satisfied ourselves that this data fell onto a scatter plot, fell onto a graph in a very nice, smooth, uppy-downy way. And why not? The data was from nature, right? If you think about it, this data is real. Like, it's very, very easy to get yourself or look up on the web. It's very steady, easily measurable data, and it does seem to go up and down in this nice, smooth, cosine way. So we're basically guessing, wait, if like the fluctuation of daylight through the year, something that has nothing to do with springs directly, nothing to do with metal coiled up, nothing to do with masses, it has to do with just like a temporal astronomical phenomena. No. But we're saying if it looks like a cosine, then I guess it smells of harmonic oscillation. Let's treat it like it is and see how far we can run with that model until it either falls apart or doesn't. Frankly, it's not going to fall apart. So we're not going to say, if this is a harmonic oscillator, let's figure out like the period of it and stuff. So we have to be careful with units here. Like 3 says, okay, we're going to measure in days, because that's the way the graph was set up, because that's what's easy and realistic and real to measure, like every day or every few days, like write down the sunrise and the sunset time. By the way, in real class, that's what I do. If we were in student class, and I actually do that on the board every day, just as a, and you can just look up www.usno.com or something like .gov, the United States Naval Observatory for this data, or just sunrise, sunset.com. You can, anyway, I'm saying this data is very straightforward and universally available. So this is all like real. Hopefully that's what makes it a little bit more understandable or concrete. It also makes it a little bit more messy because it's real. But anyway, we're going to measure the period of this now. We're going to measure it in days, because that was my point, because that's what the data is plotted in on this plot, is in days. So how can I do that? Find T, the key point, the period, right? Well, I could actually just eyeball it straight off the graph, and that is completely legitimate if you think there is enough, like, we're really asking how much time does it take for the data to sweep through a full cycle. If you go back to page 12 and just look at the picture, it looks like a full cycle takes about a full cycle, roughly just eyeballing it, takes somewhere in between 300 and 400 days. And I'm saying just eyeballing, like, how long does it take the graph to go from some point, like I just looked at the x-axis where the graph, I just looked at the y-axis where the graph starts, the purple dots, and I just followed it with my eye until the purple went all the way up to blue dots, and the blue dots fell all the way back down to where it started, to the black. And I'm just saying, how long did that take? Well, it took somewhere in between 300 and 400 days. I'm going to do this more rigorously in a minute, but it looks like it's somewhere between 300 and 400 days. And is that really a surprise? No, if you think about it, I'm going to say, I think it's approximately, probably 365 days, right? If this data is what I think it is, it takes about a year for us to cycle through the 4 seasons, which is to say, to cycle through a full lengthening and then shortening of daylight hours, as though on a spring. Okay, just looking at this picture, I'm guessing it's about 365 days, but can I do better than that? Well, the other way I can do this is, the other way I could do this is through omega. I'm just seeing if it, oh yeah, and that's what's, oh no, that is the way I'm gonna do it now. I'm eyeballing the graph, saying, look, just looking at this data, period is about 365 or 360 days. That's 3. Now I'm going to convert this in question 4. It says, It says now we're going to convert this period into a frequency. Still measuring in days, so technically this is not hertz yet, but I'm saying standard frequency by definition is the reciprocal of period. That is, if it takes approximately 365 days to undergo a full cycle, then that means the number of cycles per day will be about 1/365th, right? Cycles per day. So in other words, the standard frequency of this, if this thing were a mass on a spring, or either way, if we want to know how many cycles per day does this phenomenon take, the answer is approximately 2.73 times, I'm just doing it in scientific notation because that's the kind of guy I am, times 10 to the negative 3 cycles per day, right? Now, so that's an answer to question 4. By the way, this whole thing is a raw, me just going through the test live for you best I can. Now, if there may be errors, I'll find next, or you may have questions, of course. I will say that if any errors, I will update and correct once found. But if you're at the point of understanding where you see errors or inconsistencies in what I'm doing, and you know they're there, then that's good. That's a tribute to, that means you're in good shape. If all of this is making enough sense to reveal its moments of nonsense. So question 3 was that I got the frequency, but measured in cycles per day, again, because that's the data I'm working with. Now I'm going to come along and convert those days to seconds, in effect, so that I can get this measured in hertz, so that I can start working with it in a standard mathematical way. In other words, if the frequency was that, then the standard frequency will equal this. I don't have room to write this. I just want to convert from days to seconds. So wait, but I'm not going to. All right, times what I want to say here is 1 day over 2. See, I want to say that 1 day is the same thing as 24 hours. Right, and 1 hour is the same thing as 60 minutes. And this is a long, I'm just trying to be careful about this conversion, because unit conversion always bothers everybody if it just comes up when you're not expecting it. And it's always sort of, the issue is always like, well, I know the conversion factors, but do I divide or do I multiply? So I'll show you the way I do it, which is this. I'm dragging it out to as many steps as possible to be able to show people, if you already do it your way and you can get it right, don't worry about this. I'm not saying you have to do it this way, but I'm saying if I want to convert cycles per day into cycles per second, which is my goal here, then in principle, what I have to account for the fact there's 24 hours in a day, there's 60 minutes in an hour, and there's 60 seconds in a minute. And I think everybody knows that. But again, the question is like, wait, do I multiply or divide? Especially since the thing I'm trying to convert is in the denominator, right? I'm trying to convert from cycles per day to cycles per second. So the fact that the thing I'm trying to convert is in the denominator, that really throws people for a fair good reason, including me. So what do I always do when I have to do multiple unit conversions in one problem, when I have to do this stoichiometry thing? What I always do is I just multiply by the well-chosen one. I get very religious. I'm always multiplying. The whole thing is I always multiply. I never divide. I always think of it as multiplication. I always take my unit conversion factor and I always multiply it. But how? I always write it in a form that is equal to 1, right? Like 1 day is the same thing as 24 hours. So writing 1 day over 24 hours is like writing X over X or Y over Y or 7 over 7. It equals 1, right? That's why I'm allowed to do it, because it doesn't affect anything. So I write it that way, but how do I know which to write on top and which on bottom? I just always put the thing that has to cancel out where it needs to go to cancel out. In other words, days are in the denominator of the original. So I put days in the numerator of my conversion factor. That's how so that it'll cancel out. Then again, with hours, I put them so they cancel out. And I put the minutes there so that they cancel out. So I'm going to be, and so this is how I know whether to multiply or divide. I always multiply, and I always multiply by something that equals 1, but I just decide what's the numerator and what's the denominator by looking to see what cancellations I need, if that helps anybody, I don't know. So, but now this says ultimately that on my calculator, I better take the frequency that we had, which was 2.73. This I'm doing on a separate calculator. Sorry, I can't, like, I'm sure you can. Where is, I just lost the button. Where is, I totally apologize. I cannot find. Oh, okay. 2 times 73, 2.73 times 10 to the negative third. Okay, and that's pardon me, 2.73 times 10 to the negative third. Okay, here we go. Right. Now we want to divide that by 24 just because of the way I ended up writing it. And we want to also divide it by 60. I should probably, well, in fact, I better be careful with parentheses, right? I don't know how to use this calculator if anybody was wondering. Oh, okay. And then divide by 60 and then divide by 60. Okay, so we get that f is, of course, hopefully better be a very tiny number. It's approximately 3.2 times 10 to the negative 1, 2, 3, 4, 5, 6, 7 to the negative 8 cycles per second, which is to say hertz. Okay, tiny number, but a totally reasonable one. We're doing in the 100 millionths of cycles every second, because it takes a full year to do one cycle. So there's better be a small number, right? So, but that's the answer in hertz for okay. Hold on, sorry. So that's the frequency in hertz, and we now want to get, we have that in hertz, so we want to now convert it by 2 pi radians in every cycle to make it an angular frequency. So we're doing oh, 6 is asking us to get the full equation now. In other words, it's almost skipping a step or asking us, making sure, oh, it's giving us a hint and says, look, now you've gotten a lot of, you've gotten standard frequency, so you're in a position to get angular frequency, and you can look at the graph to get P naught, it's saying. So you're in position to get the full cosine-based function for this thing. So go for it and do it. All right, but and I will. But that means we do explicitly have to get this omega first. Finding. Okay, omega equals. In other words, for every cycle you make, you are by definition experiencing 2 radians. So the angular frequency is just 2 pi times whatever we just got, 3.2 times 10 to the negative 8th hertz. Okay, so omega, these are all approximate, I should say, equals approximately 2.014 times 10 to the negative 7th radians per second. So, and I'm sort of leaping from, I mean, technically, remember, there's a unit conversion going on here. There's 2 pi radians per cycle. So what was in cycles per second is now in radians per second. And I skipped the unit conversion, I apologize, but it's there, like in other words here. That's where the unit conversion happened. Okay, so that's omega. We now have omega. What is P naught? Well, P naught, I'm going to read straight off the graph, or you could actually, now that we have omega and we have phi, but now we have everything else, you could actually just write out the equation, pick a point in the graph and solve for P naught. It actually comes to the same thing. But it just seems to me, looking at the graph, P naught, the initial value of this whole thing, is around negative 12. And that's in units of percentage, as the whole answer is supposed to be. So I think ultimately our answer here, and this is all just a means of making sure we understand from every possible perspective how these harmonic functions work. But I think what we've got here then is P approximately equals negative 12. Again, I read that straight off the graph. I just looked, what is the value of P at time equals 0? So it's negative 12 cosine, and then our angular frequency number, which I've now forgotten, of course, 2.0, okay. So times 2.0 times 10 to the negative 7th. Oh, and then we got to put in, I'm going to have to write this more neatly. I apologize. It's not an error. I'm just writing it more neatly, more small, because we're going to, all right, P approximately equals negative 12 times cosine of whatever that number was, 2.01 times 10 to the 7th T. And I don't think we need to put in a phi at all. We've already counted. Technically, we could say that P equals 12 cosine and then put in a phi of pi over pi, right? Because this thing happened to start in a negative value where we usually assume things started in a positive value, but we've already taken that into account by putting a negative sign before the 12. So I think it's fair to leave phi as 0. So I think this is our answer. Okay. And that is, oh, and this is written in measured in like, this is the function for P having converted frequencies and periods all the way down to the level of seconds, whereas the graph spits it out in days, right? So if we could also alternately, we could give a different answer where omega is measured in cycles per day, which would more directly refer to the graph. I'll accept either answer. But let's move on from that. So that's the answer to that. Then brings in the moon. I think it's time to change the color here. Okay, so what's happening with the moon? Continue to assume that phi, oh, it even told us to assume that phi equals 0. Okay, great. Derive a complete expression for Q now. So now we're going to talk about the moon based on the new graph that we just got, which is in black. If your screen is color. All right, it says here that assume phi equals 0. There's a little contradiction and messiness in the problem here. It says phi equals 0 sort of to, oh, here it says phi does not equal 0. Oh yeah, okay, I guess that's true, it doesn't. All right, but the first thing is, so we want the function again for the moon. How do we go about this? Well, first of all, both just looking at this data, like it takes, when the moon goes through a one full cycle, let's even say a half a cycle, when the moon goes from the beginning of the graph on the y-axis up to its peak, assuming that the graph again is its minimum, for it to undergo a half cycle, to go from minimum to maximum, it looks like it goes through about 6 sun cycles. Other way around, I'm sorry. For the sun to go through a half cycle, it looks like the moon goes through about 6 cycles, if you just count on the graph. And similarly then, for the sun to go through a full cycle, it looks like if you just extended it or extrapolated it out in your mind, the moon goes through about 12 cycles. Oh, well, that's not surprising if you think about it. If you're thinking that that's sort of true, I think you're on the right track, because there are 12 months in the year, i.e. there's roughly 12 cycles from full moon back to full moon again for every one cycle of seasons. Like all these things are actually happening. The sun is harmonically oscillating while the moon harmonically oscillates in terms of its impact on us, measured this way. And if you really think about it, you already knew way before looking at this data, but the data suggests that for the moon, the frequency is approximately 12 times the frequency of the sun. So I'm almost ready just to write down the graph, the function for this moon graph. I just have to adjust for P naught. P naught, it looks like here, the a little harder to extrapolate. It looks like P naught is around -40, like the minimum of the whole thing. I'm going to say that, I'm going to be rough and ready about this. You may have a better, more precise view. I'm going to say this quickly because I don't want to dwell too much longer on this, but it seems to me that P naught is approximately, just eyeballing the graph, in other words, I mean, by definition, P naught equals the value of P when T is 0. So that's what I'm trying to eyeball off the graph, but it is a little eyeballish because the green function doesn't continue all the way, but I think it intersects around -50, let's say. So P equals around -50. Right. Okay. And so I think the function is -50 cosine, now 12 times that other, the frequency is now so it's going to be about the other frequency, the old frequency was like 2.0 times 10 to the -7. So we want like 24.02 times 10 to the -7, which means 2.4 times 10 to the -6 T. And we're saying phi. Oh. Okay, and phi, well, I was wanting to believe that. Looking at the graph, I think phi, I called phi 0 again. I think, yes, that's the error I wanted to point out. I think in the question when it says, this problem is honestly, again, it's there because it's real, because it was a problem on the last exam. So, you know, I'm trying to be realistic and stuff. It's a little heavy on complexity, this problem, unnecessary complexity. So I'm going to say right now, wherever the problem was screaming at you that you should assume that phi is not the same thing for both functions, it's enough already with this problem. Feel free to assume that phi naught essentially equals 0 for both, and let's not get too bogged down in it. So I'd say that the function for the moon, what we just wrote, the function for the moon is like this thing, -50 cosine of 2.4 times 10 to the -6 T. Okay, this is Q. Sorry, this is called Q when we're talking about the moon. Okay. right? So I'm saying, to be clear, thus I'm saying the answer to 7 is Q of T approximately equals negative 50 times cosine of 2.4 times 6. I mean 2.4 times 10 to the negative 6 of T times T. Okay, that's what I think the answer is to Q is good enough. And let's go, that's for question 7. 8, all right. Then 8 asks you to label the points so that you can understand what all this is doing. 8 says, and all this stuff, I have to admit, I find all this stuff that the question is asking independently very interesting and hopefully maybe educational or inform some of you. But of course, it is a lot to be thinking about in the middle of a live exam. But this isn't live, so I guess that's the trade-off. So when it says, and a lot of it is not assuming that you already know things. It's assuming that if you just patiently go step by step with it and allow it to guide you, that you'll figure things out. I mean, kind of like a good, well-written video game or something. But so we got this graph of the sun that looks like, and it says label points that we refer to in English as the solstices and equinoxes. Well, look, to get straight to the this is it. I'm just going to do this and maybe it'll give perspective if you didn't know. I'm not saying you already knew. I'm saying you sort of can figure all this out when you are forced to sit and put all the pieces in front of you. This is what these words all mean. And these are both the equinoxes. How do I know which one is which? Well, the equinox that's on the way towards summer is the spring, or in other words, vernal equinox, and the one that's on its way towards winter is the fall, or in other words, autumnal. So those are the 4 points we're talking about. That's what that graph means. And then it says, look at the moon graph and label the points there. This is now 9, question 9. So we're looking at the moon graphs. Well, what those moon graphs mean is, oh yeah, right. So this graph of the moon goes like this, right? Like a lot of times, every time the graph is here, here, here. I mean, they're supposed to be all the same. I just sketched that very quickly. All those are new moons, so to speak. In other words, when the moon disk is not illuminated at all in the sky, when it's like totally dark or the teeniest sliver, right? All these are full moons. And this whole business cycles the same way the sun does. I'm not, again, assuming that you already know or care about astronomy. I'm just trying to show you here how these phenomena come together and make sense once they all share the common mathematics that we are here learning. Because these are all full moons, the ones in the middle are like half moons, whether on the wax or on the wane. And just so you know, if you don't care, the reason that our calendar is so messy and weird, the reason we have like 365 days and a quarter, but it's divided into 12, but not exactly months, but then each one of them is like 30, but 31, but 28. All that messiness is the result of a huge amount of history of various attempts to reconcile something that's fundamentally irreconcilable, which is just this, that the number of times the moon cycles in the sky does not fit evenly into the number of times that the sun cycles through the sky past our perspective. The sun is a good clock because the seasons dictate our economy and agriculture, etc. And the moon is a good clock because you can freaking see it in the sky without blinding yourself, i.e. it goes through very visible cycles. So the moon makes a great calendar, the sun makes a great calendar, but the two are not easily coordinated, and that's why everything's always so messy when we attempt to follow both, as we do in the modern day Gregorian calendar. All right, anyway, that just, if that puts any perspective, but that's, I just said that. That was question 10. You won't be asked that tomorrow, I promise. I mean, yeah, you won't. Okay, that's 9 and 10. All right, now that was a lot. We could shift gears now, go to the next problem, and I may take a break and just post this recording, but we may not do all this in one recording. Oh, this next problem actually, wait a second. The next problem is the one we did do in class. as a matter of fact, I'm going to skip that for now. I gave that solution in class last Wednesday. I'm not saying it's perfect, but it's also in many lectures already in this collection of recordings from last semester. So I'm actually going to skip that problem. Eeks, something weird happened. Well, I'm going to go. Oh, and that's good because then that means there's only one more problem to do. All right, then there's only one more problem in this test, I think. And sorry, it came out looking weird, but the very last problem, which is supposed to be part 4, very last problem is, well, at least we're going to do, we'll at least do part A right now. It's vector cross products and dot products. Now, again, I never actually finished giving you a live lecture on cross products. I sort of did, or I got halfway through dot products and not further. So this may be tricky for some people. Again, however, the lecture that I would have given you is recorded and posted here, so please check them out. But I'm going to assume for right now that you know something about dot and cross products, at least their definitions, so that I could just do this, be done with it. And I'll leave the part B for later. I might even just formally withdraw it from your exam if I don't send it to you later. Okay, part A. So we've got these 3 vectors defined. Like this A is defined to be 5i minus 10j plus k. And these are all according to the definitions of I, j, and k, which I did give, which we did talk about, which may be new, but worth knowing. Okay, these are 3 vectors. And then we've got this scalar quantity, which is just the number 3, which is totally fair. Like D just stands for the number 3. It's like a constant. All right, so 1, compute the dot product of B and C. Okay, I'm gonna do that next page. Okay. By definition, the dot product of 2 vectors is, this is one way of getting it. If you know the angle between the 2 vectors and you know both their magnitudes, just multiply the magnitudes, multiply by the cosine of the acute angle between them, you're good. However, here, we don't explicitly know that angle. We could totally get it. But we're presented with these vectors in a new format that's very convenient for some contexts, not as convenient for others, but it's the one we're learning. So we've got these vectors expressed as polynomials, as sums of unit vector products, right? So the most direct way to get the dot product of 2 vectors expressed like this, is to go back to the definition. Remember, the dot product between 2 vectors, it returns a scalar. It is a measurement of 2 vectors, which it takes into account with equal weight their magnitudes, but only to the extent that they lie parallel with each other. Dot product measures the extent to which 2 vectors are aligned. In short, it only actually cares about like or parallel components of each vector. To see this formally, I'm saying, okay, let's compute B and C. Well, say I didn't know anything about the dot product, except, say I didn't know anything about the dot product except how it worked in the simplest of cases. In other words, take the unit vector I, dot it with the unit vector I. Now, what do I get? This is where we left off last Tuesday night or something, and I asked you to think about this for the next class. Based on the definition of I hat, the unit vector I means a vector with magnitude and direction. Its magnitude is necessarily 1 because it's a unit vector. Its direction is pointing directly along the x-axis because that's what we call I hat. I mean, that's what I hat means. So the dot product of this is in effect 1 times the cosine of the angle between the 2 vectors. The 2 vectors are the same. I'm dotting I with itself. So the cosine, so in other words, I'm saying that I'm dotting something with itself. So the angle between it and itself is 0. It's as parallel to a vector as it could be. It's parallel to itself. So I dot I is necessarily 1, okay? It has to be, it always will be. Not just any vector, but I hat. And similarly, by that reasoning, j dot j must equal 1, k dot k must equal 1, I dot j will equal 0, because the angle between I and j is necessarily 90 degrees, right? These are the three unit vector, the three axis unit vectors. So they're necessarily perpendicular to one another. So any two that you pick that are different, j dot all will equal 0. This is, strictly speaking, this is called an orthonormal set. But why do I care? Why do I care? If I believe all this, if I believe that this is how the unit vectors work, if this is all I know about dot products is how dot products would result in the simplest of cases, i.e. unit vectors, then that's all I need to know. If vector A dot vector B must equal, so A dot B must by definition equal remember, each vector itself can be thought of or written as a sum of three component vectors, and that's what we have here, right? So A is being written, we happen to know the numbers, I'm going to put them in a second, but A is written as a sum of three products. We're dotting that sum of products with the sum of products B, right? So B also is some number times I hat, some other number times j hat, some other number. Right, we're dotting the vector A with the dot vector B. In this case, if we remember now, in this case, I'm just opening up my other thing. I forget what they're. Okay, if in this case we're saying, well, actually, let me take it one step further before I even apply in this case. Notice then, if if I dot two vectors, if I think of each vector as a polynomial, if I think of each vector as a trinomial specifically, as a sum of three products, well then to multiply this whole thing out, if we're truly talking about some form of multiplication, what I'm really saying is FOIL, right, or distribute, however you want to say. I'm going to do, the first times the first, plus the first times the second, plus the first times the third, plus the second times the first, blah, blah, all the combinations, in other words, right? Like I'm distributing everything. So I don't care what the actual vectors are, if you really think about it, if you FOIL this out, so to speak, you'll get A X I hat dot B X I hat, right? Plus A X I hat dot B Y J hat. You see what I'm doing, right? I'm like the first one times the first, then the first times the second, then the first times the third. I'm just expanding out this whole, product of two trinomials. So this plus, by the way, if I circle something like this, that's what I sometimes do to make it clear that one equation is going on to multiple lines. That's what's happening here. So we have bleh plus on the next line, bleh plus on the next line, A X I now dot, hopefully you see the pattern, B Z K. Okay, that's all that. Plus, so this is looking very complicated. It's going to be 9 things, right? But don't worry, we're only going to have to do it once, because now it's plus A Y J times B X I plus. Now this is getting very cumbersome, right? And I'm probably losing everybody's interest, including mine. But maybe I don't have to go too much farther to realize, wait, a pattern is emerging or something's happening. Like, let me stop for a second. I hope you see the pattern I'm doing. I'm doing it for a reason, because I do have to get the answer. But look, up here I have AXI hat dot BXI hat. Let's just stop and like, can we even deal with that term? Yes, we can. That would just be AX dot BX, i.e. AX, BX, like they're just numbers, times I hat dot I hat, right? I mean, multiplication is commutative. So if I just rearrange that term, I hat times I hat, we already said was 1. So this first term reduces to AX, BX nicely, as it should, because it's basically just saying, look, just look at the the x component of the first vector and dot that with the x component of the second vector. Well, they're necessarily parallel because they're both just x components. So when you multiply them, you should just, when you dot them, you should just get the product of their sizes, as it says here. But then the next term, right, I hat dot I hat is equal to 1, I'm saying. And that's what I needed to figure out the second term. We now have I hat dot j hat. But I hat dot j hat is 0, right? Those are perpendicular, they cancel out. So this thing is 0, this thing is 0. And in other words, we could write down all 9 of these terms. There should be 9, it's 3 times 3. But the only ones that are going to survive are going to be the multiplications of the like components. And those are going to survive really nicely and cleanly. We're just going to get simple multiplication. In other words, wherever the dot is not 0, it's going to be 1 between unit vectors. So I think at the end of the day, you can always count on that if you have 2 vectors and you're dotting them, it is always true that the answer is this. That is always true. 2 vectors being dotted, you'll get that. But you don't always know theta. You sometimes have them written in different form as we do here. So what this is equivalent to, we just showed, what is equivalent, and it just depends which context, is to write right? In other words, the dot of 2 vectors, this makes it look as it should, I think. The first way says you only multiply parallel components, in effect. This says the same thing in a different language. This is saying the dot product of any 2 vectors is the product of their x components times the product of their y components, plus the product of their y components plus the product of their z component magnitudes. I'll just add it together to get one big magnitude. It doesn't give any more weight to any of the components than the other, but it also doesn't retain the information, right? In the end, the dot product is a sum of products, meaning it will only take into account how like components are being sized, but it will account for them all with equal weight. But once it puts all those components together into an answer, as it does, after it takes into account the x components looked at separately, the y components looked at separately, and the z components looked at separately, it gets those 3 separate, equally weighted, independent answers and adds them all together to get one number in the end, which conveys nothing about how those different components were apportioned, right? In the end, we're going to get a scalar quantity, not something that favors or indicates any direction, as we should for the dot product. In this case, that is to say, and I have to bring it up again, sorry. Okay, in this case, that is to say, 5 times 4 plus -10 times 4. Whoop. Ooh, sorry. My total bad. I was just seeing if you were paying attention. No, sorry. In other words, the I component of vector A is 5, but the I component of vector B is 0. There is no I component of vector B. So it's 5 times 0 plus -10 times 4 plus 1 times -4. Right, you see what I'm just looking at the components, the like components of the individual vectors. And in other words, that will be -44. I'm saying that A dot B equals, okay, -44. And we're going to wrap up in just a few minutes when we finish this problem. And first, I'm going to look at a word from my spiritual sponsor. And I'm even going to shout out to my spiritual sponsor. Awesome, thank you. And by spiritual sponsor, of course, we mean something in between the Spectre Galileo or my wife, you decide. All right, so the dot product of A and B is equal to -44, and that's like literally an answer. Let me make that very clear. We're looking for a dot, we're looking for a dot product, and a dot product should in the end just be a raw number with no I hat, j hat, or any directionals at all. It's not a vector anymore, it is a number. That's what the dot product does to vectors. So that's question 1 of this part. We're moving on here now. Now we get to cross products. Now that is a longer lecture to actually explain. What I'm going to do here, and again, that's available. I'm not going to do that explanation now, perhaps later, but I will just assume that you've seen it or something, or when you're up to the stage, and I'm going to write out how it applies here. So just like so far we have So I'm just telling you, we're on to, this is all supposedly part 4. I don't know why that, this is all part 4 of the exam. In other words, page 20. Part 4, and of that part A, question 2, the cross product. And this is all, I'm talking about page 20 of the practice exam. All right, question 2, the cross product. It's asking us to do the cross of A and B. In this case, it's given us the vectors A and B, but the real question, and they're nice, straightforward vectors, they're arbitrary. So if we can do it here, we can do it for any 2 vectors. So the real question is, what do you do for any 2 given vectors if you want to cross them? Now, I'll quickly say the cross is like the opposite of the dot. It's not strictly an opposite, but it's the other side of the multiplication coin. The cross product is what you do when you want to measure a relationship between 2 vectors, which takes into account not only their relative magnitudes, but their relative directions. You want to measure a relationship between 2 vectors that looks at how big they are compared to each other and looks at how directed one is compared to the other. Put another way, you want to look at how much they differ in direction. If they didn't differ in direction, if they were parallel, then there's no need to use vectors at all. They're like numbers on a number line. And that's the whole purpose of the dot product, to reduce situations in that direction. But if we want to take into account how one vector differs directionally from another, then we use a cross product. And then in order to retain, track, or convey that information about direction, what happens is we get an answer in the end that itself is a vector. Our answer to any cross product between 2 vectors is going to be a vector, which itself has both magnitude and direction. The magnitude will indicate something about the relative magnitudes, and the direction of our final vector will in fact be directly dependent on, and therefore directly communicate, how the 2 directions differed in the first place. I'm saying this quickly again because supposedly this is a synopsis, but what that means at the end of the day is that we're measuring perpendicularity, not parallelism, when we measure a dot product. And if given 2 arbitrary vectors, A, like let's say there's some vector A that points like that, and some other vector B that points like that, given, so in other words, they are separated by, whoops, oh yeah, the smallest possible angle that separates them, let's say, is theta. And we can see that when we draw the 2 vectors tail to tail, right? If we're given this situation, then what I'm saying is the cross product of these 2 vectors will yield a vector. So, so whatever answer is going to be a vector answer. I'm going to first say that the magnitude of that vector that we get, okay, sorry. So let's say, so I'm saying if A cross B, if we just give the name C to the vector that is the cross between A and B, okay? I'm doing this for a reason. Say we call it C just so we can track it. Then I can't make some simple statement like C equals AB sine theta or cosine theta like I did before, because again, C is a whole vector. It doesn't just have a magnitude. It's not going to be as simple as the dot product was. But I certainly can start by saying something about the magnitude of the C vector. The magnitude of this vector, the magnitude of the vector I get when I cross 2 arbitrary vectors, the magnitude will be as perhaps you would expect, or maybe I want you to have expected. It will not be A times B times cos theta, because cosine of 0 is 1, and cos is what we used when we were measuring parallelism. It's going to be the other choice. It's going to be AB sine theta, where, in other words, if theta, the sine of the angle 0 is 0, and the sine of pi over 2 radians is 1. So this is going to flip things. We're going to get major maximum magnitude when 2 vectors are as perpendicular as they can be. I mean, when they are perpendicular. We're going to get no magnitude when they're parallel. This is trying to indicate this vector is going to be bigger and bigger if the 2 vectors in question actually are differing directionally, i.e. if they're allowing direction to play a role, if like they require direction to be taken into account, were they to be identified. So what's the direction of this final vector going to be? I'm going to have to say that very fast, but the direction of the answer we get will be a direction dictated by what's called the right-hand rule. In other words, this is the rule. Given any two vectors, A and B, okay, the right-hand rule says, again, saying we're going to need either, you need to look at this somehow, not just right now, but the right-hand rule says you take your right hand, you place your fingers along the first vector, A, curl them, curl fingers, towards the second vector, B. I mean, direction matters. I mean, order of operations matters here. The cross product of A with B is actually going to differ from the cross product from B with A. So if you're taking the cross product between two vectors, A and B, you put your fingers along A, then you curl them towards B, wherever your thumb, as long as this is your right hand, which it must be, wherever your thumb is pointing, that is the direction of the answer to the cross product between A and B. There's reasons for that. I'm going to try to talk about this more in class if I can, or again, see the other lectures. But if you think about it, it really does make sense. All of this is a convention to help us just all make sure we're self-consistent with plus and minus signs. What it's really saying in English is that if you cross two vectors and you get a vector, what you're measuring is how perpendicular the two vectors are. So the answer you get, if you really think about it, must be perpendicular to both of the vectors that you were looking at in the first place. And that, in fact, is always possible. And there's actually only one axis ever that allows for that. That is, whatever two vectors you have, they form a plane necessarily. Any two vectors, two lines, uniquely determine a plane. So the answer, according to the right-hand rule, according to the cross product, the answer to the cross of some A and some B that are in a plane will be a vector that is perpendicular to that plane necessarily. Otherwise, it would be closer in angle to one of the two vectors and in effect give more weight to one of the two things being multiplied than the other. The only way that our final answer can take into account direction fairly from each one and account no more for one vector than the other is to be the same angular distance from both. It can't be 0 from both because then it'd be parallel to one and not the other, but it can be 90 degrees, pi over 2 radians from both, as long as it's perpendicular to the plane. So the answer to the cross product is always perpendicular to the plane in which the two original vectors were drawn. The only question is it out of the plane or into the plane? And that's decided by convention, which is called the right-hand rule. Like, it doesn't actually matter what the answer is as long as one is self-consistent, but one also wants to be consistent with everybody else to not get confused. So the thumb gives you, curl fingers towards B, and your thumb will give you the positive direction along the axis of the answer, the axis perpendicular to both planes. And if it's going into the plane, and since these things are vectors, which are signified by arrows, we pretend we're looking at arrows. If you looked at an arrow flying away from your eye, we imagine you would just see the tail feathers at the back edge of the arrow. And we imagine that if you saw an arrow coming toward your eye, you would just see the tip of that arrow. So in other words, if you draw this, it's supposed to indicate out of plane of your computer screen or of the blackboard or whatever. And if we draw this, it's supposed to indicate into plane. It's the best. And when I say we, I mean like all physicists. It's primitive, but it's best we can do with 2 dimensions. That's what I could say about the cross product. But in other words, to sum, and we're really almost done because we have to be. So far, what we have is that if you're given A and B, then A dot B is necessarily going to be equal AB cosine theta, end of story. The cross product is not that simple because it's a magnitude and direction, but we can say this. And we can say, this is all what we're saying so far, like the magnitude will be AB sine theta, the direction will be right-hand rule. So what does that finally mean? What it finally means, it means if A and B are written if A and B are written in the form that we have today, if they're not written in terms of theta, but if A is written like this, as it is today, some amount plus some amount plus some amount. If this is the way A is written, and this is the way B is written, again, I'm using that circle to mean on the next line. I'm being inconsistent about which line I put it on, but it means the same thing. If this is true, if this is the kind of vector presentation we have, this is, it's just like how notation can just really get in the way if you don't know. If the vectors are notated in this fashion as sums of product, then to cross them, we do the same thing as before. We FOIL out the whole thing, right? And we look for I, J, K, unit vector cancellation, simplifications. That's exactly what's going to happen here. We're going to try to do so. Then A cross B must equal, okay, go term by term. I'm going to go until I see a pattern. A X I cross B X I plus A X I cross B Y J plus A X I hat cross B Z K hat. Okay, et cetera, all these 9 terms. Now what's happening when I do this? Well, like, I'm just going to look before. I know what's happening with I, J, and K vectors. We have AX I hat cross BX I hat. Oh, well, I didn't. What's I hat cross I hat? I'm going to cut straight to the chase and say that it's 0 because it better be one, like the magnitude of it had better be the magnitude of I times the magnitude of I, and I don't mean the imaginary number, I mean the unit vector here, times the sine of the angle between them. Well, that would be 1 times 1, but times 0, right? In other words, a vector is parallel to itself. It's not at all perpendicular to itself. So if you cross a vector with itself, you get 0, right? In sum, and this is, so I hat cross I hat cross I hat must always equal 0. Similarly, J hat cross J hat must always equal 0 in the case. But I hat cross J hat, now what does that equal? Definitely not 0. It does equal 1 times the sine of the angle between them, which is 90 degrees. You're probably seeing where this is going. But now let's be very careful. The magnitude of this will equal 1 times 1 times 1. Yes, if you cross I with J, you're going to get a vector whose magnitude is the full-bodied 1. Good if you already guessed that. Definitely awesome. But we have to, no error, just here. But that's just the magnitude. If you cross I with J, you're going to get a vector whose magnitude is 1, but then points in some direction. What direction? I have no idea. Yes, I do. Right-hand rule. If I put my fingers along I and curl them towards J, where's my thumb going to point? Along K, positive K to be specific, right? In other words, I cross J equals, I hat cross J hat equals K hat. J hat cross K hat equals I hat. If you think about it, and you have to think about it, you have to try it with the right hand, and I recommend it in private, and I don't mean that weirdly, I have to, but it's very embarrassing in the middle of an exam to be figuring out this right-hand rule thing for the first time. Like it's both awkward and it doesn't work exam-wise. Like you have to get used to this if you haven't somewhere else in your life already. But J cross K will then equal I, it cycles around. But what about like K cross J? Well, this whole thing is anti-commutative. If you're using your right hand, curling your fingers from the x-axis to the y-axis, point your thumb along the z. But if you move your hand, curl your hands from the y-axis to the x-axis, your thumb is going to point in the opposite direction along negative z. And we're taking that into account. This operation is technically anti-commutative. So K cross J equals negative I, et cetera, et cetera, et cetera, et cetera. Now I'm going to use that right here, and we are almost done, kind of, sort of. I'm going to say then, then AXI cross BXI certainly will always equal 0, but like I mean AXI hat. Every time I say one of these, I do mean hat. AXI hat cross BYJ hat, what's that going to equal? That is going to equal AX by times k hat. You see what I'm doing? And I'm going to do that for all the terms. If I had something like ax j hat cross b y k hat, I hat, if I went backwards, in other words, then I would say that the answer is negative ax b y k hat. You see what I'm saying? But the answer to a cross product has to be a vector. So it has to have direction. No simpler, faster, more direct way to express direction than with a unit vector. That's why we're using them. So if you do out these 9 terms, you're going to get 9 terms, and then you're going to be able to group them. I'm not going to do this right now, but I'm telling you, if you do out the 9 terms, then you'll see, you can collect like terms, and you'll see that you have a couple of terms that have I hats after them, a couple that have J hats, a couple that have K hats. And if you group them all accordingly, you will ultimately get this. And you should test this on your own. You should really do this to make sure you see what you'll never be able to just memorize this if you don't get it. I mean, you can try, but it's just so junky. You're going to get, it's long. You're going to get this. This all is the I hat, plus you'll get that's the J hat. There's a pattern to all this that, of course, now I know, so I can sort of, and you'll know if you look at it, but you to see it, you got to do it out. I'm telling you. You're not arguing, so why am I arguing? You're not even there. Okay, ax by minus ay bx, and that's all in the z-axis, i.e. k hat component. We're almost done. So this is in general true. You can memorize this if you want. Like, it's always true. It's just such a mouthful. Believe me, I now do remember this because I use it all the time, but I never tried to memorize. I probably tried, and it was a dumb idea. If I've memorized it, it's by accident, not on purpose. And I recommend that. Okay, so we have this, but now we're going to apply it to this problem, and then we can all get out of here because there's life to be led by somebody, one of you, I hope. So right, so here, A plus B equals. All right, I'm going to do this out now. So first I have to do AY times BZ. So AY, so I do negative 10 times BZ. BZ is negative 4, okay, so times negative 4. Okay, I do that. Minus AZ, that's 1, times BY, that's 4. Okay, that monstrosity is my X component. Like, all that is how much I go along the X-axis, i.e. times I hat. Then I do, the next component is going to be, and again, I'm saying this, I'm just looking to memory. You have to look back a page to see what I'm doing. But I'm going to do AZ times BX. AZ is 1 times BX. BX is 0. Good, so that'll cancel. Minus, now AX times BZ. AX is 5. BZ is negative 4. Okay, all that is my Y component, my J hat. And finally, the last component, I'm going to do AX, which is 5. I hope I didn't do this wrong. AX, which is 5, times BY, which is 4, minus AY, which is negative 10, times BX, which is a 0. Good, I was hoping for another 0 there somewhere. And we get X. Now I quickly scan to see if I have any, I scan my parentheses to make sure that nothing in my parentheses is a repeat. If something is a repeat, it's a good chance that I just messed this up, right? Because you're really just doing out all the different combinations. But it doesn't look like I blatantly messed it up. So I'm just scratching this up here so you can see. I'm going to get, and we are almost there, ladies and gentlemen. I mean, it's been a rough road, I know. But we get 40 minus 4i plus 20j, I'm sure I'm making a mistake here. No, check me. I'm just doing the arithmetic. And then k is 20 minus 0, so 20k. I know something is wrong here. But this is what I have. I believe the answer is A cross B, A cross B equals 40 minus 4. Can that really be right? 40 minus 4. I feel like it should be 40 plus 4. Let me just look one more time. That's supposed to be AYBZ. That's supposed to be AZBY. AZ is 1, BY. BY is 4. All right, I'm going to assume this is right. I'm sure one of you will find an error, but I think it's 36I plus 20J hat plus 20K hat. And I think that's the answer to A cross B. In order to then to do the next, we're going to assume that these operations are associative and commutative. Well, they're not commutative. We're going to assume they're associative. So to do 3 and D, you just iterate. I mean, what I just did in 1 and 2. In other words, I'm not going to solve 3 and 4 right now. I think if you follow this, they're great practice. I'll give you a little more time to practice yourself. I will post them fairly soon. If I tonight do not post anything about or regarding part B of this, or if I don't say anything about it, then you can assume that falls off the exam. Maybe fluid drag will fall in instead. I will be more clear about that tomorrow. But still, your priority should be worrying about this document. Don't worry about the fluid drag until you're up to it, the thing I posted yesterday. And your last priority in this document is this gravity problem here in part B, because I'm not worrying about that right now. And if I don't solve it tonight, then you don't have to at all for your exam. But the next 2 exercises I'll get to you later. I think you'll find them straightforward. Okay, thank you very much for listening. Again, this is all just to help. You don't. I would recommend, if you find this recording before tomorrow, I certainly recommend checking it out before tomorrow so you have questions for tomorrow, because the one purpose of this is I'm not going to straight up do this again, letter by letter, as I am here. I'll answer questions about this. Okay. Thank you all. Is there something else I have to do?